Okay, welcome back, class. Hope everybody's safe and healthy. We're going to do a t-test from start to finish. We're just going to go through it, and I'm going to let you guys do the work. So what I'm going to do is I'll sort of set this up and have you guys do the computations. What I want you to do, or what you should do, is just pause the video while you're doing the computations. Then come back to it and see if you got the right numbers here, okay? So let me set this up. This is an experiment where we have, I guess we could call it a sports psychology experiment maybe, where we have people going through an obstacle course. And these numbers represent the time that in seconds that it takes them to get through the obstacle course, all right? And we have a group that we are just going to let go through the obstacle course, 6 people, okay? And these are their times. And then what we're going to do with another group is we're going to give them visualization training. You may have heard this in sports, where we have someone talking with them. Maybe we'll bring them through the course, and then we'll say, listen, I want you to visualize yourself doing really well through this obstacle course, excuse me, and visualize yourself doing really well and winning the competition, okay? And so the question that we're asking is, if we're working with this sports psychologist, is that going to make a difference in terms of, is visualization going to make a difference? So this is what the data looks like. Let's do the first 2 steps, the null hypothesis and the alternative, and then setting up our critical value, okay? So our null hypothesis would say that no visualization and visualization will perform equally, okay? The samples that we have, we're presuming represent these populations, but they're equal. Another way to say that is to say there's not going to be any difference. If we subtract the 2, the difference will be 0. Okay? We've done this before. This is review. Alternative, that the groups are going to be different. They're not going to be equal to each other. Or we could say if we subtract them, we're going to get something other than 0. So this step should be old hat by now. Okay? And certainly on the final exam, you're going to need to do this. Okay, so that's the first step, step 1 in our hypothesis testing. Step 2, we get our alpha level of 0.05. Now in this case, let's go back to the data. So we have n equals 6 here. So the degrees of freedom for this group is 5, right? N minus 1. We have 6 people here. Degrees of freedom is 6 minus 1 equals 5. And so we have 10 degrees of freedom. Everybody with me here? 10 degrees of freedom. We're going to look up the critical value in the back of the book, and we find that the critical value, we've seen this number before, 2.228 is the critical value for 10 degrees of freedom. Okay? So step 1, step 2, old news. You should be able to do this easily. Here are the data. The word data is plural, okay? And we need to get the mean for group 1, the mean for group 2. We need to get the sum of squares for group 1. We need to get the sum of squares for group 2, okay? Remember, this is our sum of squares formula. This says square each number. 120 squared, 82 squared, 40 squared, 35 squared, so on and so forth. Add those together. This tells you add the numbers first and then square. Divide by the number of numbers, in this case 6. Okay, in this case 6. So we're going to get the sum of squares for each group. We'll get the mean for each group. So the sum of squares is going to take you a couple minutes. And so what I would do right now is pause the video and do the computations. Okay, so we're back. Hopefully you did the computations. Let's see if our numbers match. The mean for the first group is 70.67. 70.67. Okay. My marker's dying here. The mean for the second group is 59.33. Hopefully people got those numbers, right? Sum of squares for the first group is 4,875.33. 4,875.33, right? A little bit different than when we had the numbers, the single digit numbers or the small numbers that we had. We know why this is so big, right? We're taking the deviations and squaring it, adding them all up. That's old business. For the second group, 4291.33. 4291.33. Okay? So hopefully you got those numbers. And we're set to go for our t-test. All right? And here's what we're going to do. These are the formula. Okay? These will be provided on the exam, of course. Okay? And this is pooled variability. And I'm going to go through the conceptual again one more time. The computational shouldn't be that bad, right? We have a sum of squares for the first group, sum of squares for the second group. Let's do this. 4875.33 plus 4291.33, all of that divided by 5 plus 5, okay? And so let's get that number. We can do that together. 4875.33 plus 4291.33 equals 9,166.66 divided by 10 equals 916.67. 916.67. Okay? So this is our pooled variance. Okay? We're combining both groups. We're combining the groups to try to get our best guess for sigma. Now, it's actually our best guess for sigma squared, but we'll undo that up here, okay? The point here is we're trying to get a guess for sigma. And again, we're going to make our assumption of homogeneity of variance. That's an important concept. We expect that these two should be equivalent, right? Similar. 4875, 4291. That's pretty similar just because I've been around the business for a long time. So we make that assumption because, remember the two things. If we fail to reject, then both these samples are coming from the same population, right? So these should represent some good guess about sigma. So we're going to pool them together. If we reject the null, we assume that the treatment, the effect of visualization, will just push the curve around, but it won't cause any change in the variability. So no matter what decision we make, we should be able to combine these to give us our best guess for sigma. I mean, I have two guesses for a quarter instead of one, so we're going to combine them. So here's the number here. So this is our guess for sigma, okay? And then this step here is our central limit theorem step, right? This is the step that we used to go when we're going from talking about individual scores to groups of scores to sample means. So that's what we're doing here. And I'm simply going to take my pooled variance, okay, and put it in here. So it's 916.67 divided by 6 now, 6 because this is n. Follow the recipe. 916.67 divided by 6. Don't forget to take the square root. Some of you are going to forget that, and it's going to affect your test score, okay? So, 916.67 divided by 6 equals, and of course, we do that twice. So, 305.56 underneath here, 305.56. We're going to take the square root of that. So 17.48. Everybody get that? 17.48. Okay. Let me just check my numbers here. 916.67 divided by 6. Do that twice. 305.56. Take the square root. 17.48. Okay. So this is our standard error number, right? It's our standard error. It's the standard deviation of distributions of sample means. Best guess for sigma. This is our central limit theorem step. We're going to take this number. Remember, this is just a subscript here. S sub m1 minus m2. Okay. Take that number, put it up here. Okay, everybody with me? The computations, the mathematical portion of the class, as you're now finding out, is the most straightforward part. It's the conceptual stuff that's the challenge. I think you would agree. But there's lots of opportunities to make mistakes here, so we just need to be very cautious and methodical and stay organized, okay? So now all we need is the top. That numerator is the difference between the two means. Is there a difference between the two means? That's something other than 0. Now, of course, we know there's a difference, but we're going to put that in the context of standard deviation, or in this case, of standard error. Okay? 70.67 minus 59.33. Is it 59.33? 59.33. Divided by 17.48. So let's do that. 70.67 minus 59.33 equals, so it's 11.34 on the top, divided by 17.48. So our t-value is 0.65. Okay? Now, I'm making some assumptions myself here because I think you understand now what that number is. This is the number of standard errors that these two are separated by, right? We get the difference, we divide by standard error. It's not even one standard error difference, 0.65. So what do you think we're going to do with the null hypothesis? You guys are so good. I'm going to go back. That our observed t-value of 0.65 is not even close to being beyond our critical. Remember, we can remind ourselves here we have a little bit of room. .228, 2.228. Okay, does that help? Right? 5% is beyond that number. When we do our calculations, we get a value right here, right? 0.65. And so in this case, would we fail to reject the null, or would we reject the null? And of course, we're going to fail to reject the null. And we'll do our step 5, of course. We'll say it appears that visualization does not, okay, does not affect completion time for our obstacle course, okay? In parentheses, T with 10 degrees of freedom, okay? So when I'm reading this conclusion, when I read a journal article, I look at that and I know that there's 6 people in each group, right? 5 degrees of freedom plus 5 degrees of freedom, if it's equal group size. I put my observed value, folks, my observed value, not the critical. This is what I'm basing this decision on, that it was only T of 0.65. Okay? And then semicolon, P less than 0.05, excuse me. See how easy it is to make a mistake? This is P greater than 0.05 because we failed to reject the null. It's greater than 0.05. The probability that this is true is greater than 0.05, all right? That's it. That's t-test. So you can expect something like this on the final. You'll absolutely have to do a t-test, go through the 5 steps, and make your decision, okay? I want you to make sure that you know the conceptual basis of these 2 things. Pooled variability. We're going to make our guess for sigma now using both groups. It gives us a better guess for sigma, okay? It's actually a guess for sigma squared because we're waiting to do the square root till we come up here, okay? This is our central limit theorem adjustment so that we get the standard error instead of standard deviation. This ratio, like always, difference over variability, the difference over the variability. In order for us to reject the null, this has got to be more than twice as big as this. This has got to be more, this difference has to be more than twice as big as this. In this case, this difference is not even one of these, and so we fail to reject the null. Okay? That's it. So that is chapter 10, I believe, 2-sample t-test. Okay? Hopefully everybody is comfortable with that at this point. Yeah. Okay, so now I want to talk about a chapter that we're not going to do any computations here. I really am going to switch again to something that doesn't involve computations for us, just because we're running out of time, right? I mean, the good news is we only have a little over a week left of classes, but we're just scratching the surface, really, believe it or not. If you go to graduate school, especially in psychology, this course, Psych211, is sort of the first half of your stats course in graduate school. Then you go on from there. Yes, believe it or not. Most graduate programs in psychology require 2 semesters of stats. But this is going to set you up really well. So I want to talk about a research design issue. And I just want to tell you that there's another flavor of t-test, okay? So let's go back to our data. In this case, we have a group that did not go through the visualization training, and we have a group that did go through the visualization training, okay? The t-test that we just performed is called a t-test for independent measures, or a 2-sample t-test, okay? So that these 6 people are different from these 6 people, okay? There's another way to do this research, and that is if we use the same person, right? So they go through we see them go through the obstacle course without visualization, and then we see them go with visualization. So this is the same person. Let's call it subject 1, subject 2, subject 3, subject 4, subject 5, subject 6. And we look at their performance without visualization, and we use the same person. So this way, right? It's the same person after they get the visualization training. Okay? This is a research design issue. And you can do this research either way. You can have 6 people here and a different 6 people here, or you can have 6 people here and then retest them and get their measures. So this design is called a repeated measures design. A repeated measures design, okay? It's also called a pre-test, post-test design. Pre-treatment, post-treatment, okay? It's also called, and this is what we call it in research methods, this is a within subjects design, because I'm manipulating the independent variable. I'm doing my manipulation within the same subjects, okay? The way we did the t-test before, it was called a between subjects design. That is, different subjects here, different subjects here. That's called between, or it's called independent measures, okay? This is called repeated measures or pre-post test or within subjects design. It depends on what textbook you're reading, okay? It depends on what course you're taking, what major you're in. These are all pretty much the same, okay? I prefer this one, within subjects design. And if you do this design, then the t-test that we did is not the correct t-test, okay? So you have to decide on the t-test you want to do based on the research design. So if these people are a different group than these people, then what we did, or the t-test that we did, is appropriate. If these are the same people being tested again, then you need to use a different t-test, okay? And I'm not going to go through that. We don't have enough time to do that. But you better damn well be sure that you know that that exists, because if you do a research project, if you're in PT, you're going to do your master's. OT, you're going to do your master's. If you're in psych and do your master's, you're going to do a research project. And you need to know the difference between an experiment where you have 2 different groups of subjects and an experiment where you have the same subject where you're measuring them twice, okay? This within subject design. Because that will determine what t-test you're going to use. If it's 2 different groups, do the t-test that we've been doing, okay? And that's what I'm going to ask you on the final, to do the 2 sample, the independent measures t-test, okay? But I will ask you a question about this design where you're using the same people. It's called a within subject or pre-post or repeated measures, okay? Then you use a different t-test. And so I also want to talk about the conceptual basis of that t-test without going through the computations. Okay, let's see how this goes, all right? Let's look at the structure of our t-test. Let me do this, and we've done this before. In fact, I think it's probably worth doing this again. Z-score for individual scores. You look at the deviation, you put that in terms of the variability. Difference over variability, okay? Then we did samples with z-scores. And remember I said that's the same structure, the difference of the sample mean from all the overall sample means of the samples divided by standard error. Difference over variability. Then I did a single sample t-test, right? I did a single sample t-test where we pretty much did the same thing, except this is our estimate for sigma based on the sample variability. And then we finally just did a two-sample t-test where we're looking at the difference, and we have a measure of variability that was based on two samples, okay? The common feature here, it's really a common feature. It's a ratio of what? Difference over variability, okay? And we get numbers for this. We get numbers for the difference, and we get a number for variability, and we look at the ratio, and for these tests, right, 1.96, 1.96, these are going to be 2 point something, right? But basically, we want a ratio where the top is 2 plus over 1, right? This could be a difference of 20 plus over 10, or 300 plus over 150. Notice that there's no special number. I say plus because, you know, we had a critical T of 2.228, critical T of 2.201, a critical T of, you know, whatever it is. But it's a little over 2. As long as the top is twice as big as the bottom, or more, that's why I have the plus there, then we're likely to reject the null, okay? For all of these, 1.96, 1.96, and then all the 2.2 somethings, 2 point whatever it is. But notice that the top, there's no magic number. There's no magic difference. Something could be 300 points difference, but if it's 500 in the variability, then you're not going to reject the null. Something could be 20 point difference. If this is 5, then you have a huge t-value. It's the relationship between the two numbers that counts, not any special difference here. Okay, so let's go back. So we had, what kind of a difference do we have on the top there? 70.67 minus 59.33. We have an 11.37 difference on the top. 11.34, sorry. 11.34 difference. That's this value here, okay? Now, the reason that that wasn't statistically significant is because the variability is 17.48, right? But 11.34 could be significant if the bottom was, let's say, 3.27. I'm just making that up, okay? What I'm telling you here is 11.34 could be a huge difference if the variability was smaller. 11.34 could be a huge difference if this is smaller. But in this case, we have lots of variability, and so we had an insignificant t-value. Everybody with me? Okay. It's the ratio. So if this was smaller, this 11.34 difference could be statistically significant, right? If it was 11.34 and the variability was only 3.27, then we'd have a huge number out here. It would be 3 something, okay? With the same difference on top. So this is a lot of variability, It's causing my t to be small. Let's look at the data. Wow, look at this variability. Look at the variability of the time it takes for these people to get through the obstacle course. Huge. And then we did this variability. If it was different people, the way that we did it, we combine this and this, right? We put those numbers here. We got these huge numbers, and it made our t so it was insignificant. If these are two separate groups of people, we did the right t-test. But, and this is why it makes a difference if you have the same people. Same six people, okay? Lots of variability here. Let's look at the difference between these two people. Wow. Look at the difference between these two people. Wow. Lots of variability, right? But if we use the same person, I mean, who's the slowest person in this group? Subject 1, right? If we look over here, it's not surprising that they're the slowest person over here. Who's the fastest person in the group? This person here. If we look over here, it's not surprising that they're the fastest person. So some of the variability in research terms, it's called, we can account for. This is the slowest person. They're the slowest here. How much did they improve by doing visualization? How much did they improve? Well, they improved by 13 seconds. I'm just looking at the difference here, right? How much did this person improve by? 12. How much did this person improve by? 10. How much did this person improve by? 7. How about this? 12. How about this? 16. Is that right? No, 14. I can't even subtract, right? When we look at their differences, we find out that visualization really helped each one of them by almost the same amount, or at least similar, right? Doesn't matter if this was the slowest person, they improved by 13. This is the middle person, they improved by 12. Here's another one, improved by 14. So really the effect of the treatment is rather consistent, but if we did this with the between subjects and independent measures t-test like we did, all of this variability, we treat it like we don't know where it came from, okay? Now, we're not going to do the computations, but please listen, right? And if you need to, replay this, replay it, okay? The visualization is affecting each of these two people in almost the same way. Not very much variability, okay? When we do this and we act like these are two different groups, I don't know where the variability comes from. When I'm using the same people, I know this person's slow. Person's slow here, person's slow here. Person fast here, person's fast here. So I don't need to put all of that variability in the denominator, okay? So mathematically, we're going to subtract some of that variability out. This stays the same. The 11 point, I shouldn't have erased that. The 11.33 is the difference between the two means. But rather than counting all of this as if we don't know where the hell it's coming from, I'm going to be able to subtract some of that out and just look at the variability here. It ends up being that this is, you do a one sample t-test with these numbers, and if the null was true, these would be zeros. But again, we don't have time to do that. I just want you to know, two things. The difference in the design. So you could either have two separate groups of people or one group of people that's measured twice, okay? When you have two separate people, it's called a between subjects design. When you have the same people being tested twice, it's called a within subjects design. I'm doing the experiment within each subject. That's where the term comes from. And what happens typically is you can account for some of the variability. That is, you can explain some of this variability here. You can explain it. You don't have to say this person was the fastest, this person was the slowest. You know that probably will be the case over here, and so you don't need to count it twice. Okay, so this number will get smaller. This number will get smaller typically. And what will that do to our t-value? If this number gets smaller, this will tend to go up, even if we maintain this difference. Okay. Again, we're not going to do the computations. Once you get out of this class, you'll be doing the statistics on a computer. But you need to tell the computer, is this a between subjects design or is this a within subjects design? Because the computations are different for this value. Not for this, by the way. This remains the same. The difference is the difference. But we're able to account for some of this variability. Okay? So if we go back over here, okay, difference over variability, difference over variability, difference over variability, difference over variability. Okay? And what we're looking for is the top should be at least twice, a little bit more than twice as big as the bottom. If it's more than that, great. I mean, if we have a T of 5.17, that's awesome. We're going to reject the null, right? This is what we did for our two-sample t-test. You would do similar if you had a within subjects design, but this value would change. Okay, so that's all I want to do with the repeated measures with that within subjects design. The book calls it correlated T-test. I don't like that term. That's why I didn't use it. But it's when you have the same people, okay? Then you can account for some of the variability. The variability gets explained, all right? Just know that that test is there, and it will influence the difference in the computation will happen here. We're not going to do that, okay? So that's that. Steps 1 through 5, difference over variability. We do our t-test, and we're done with t-test now. So on Friday, we will talk about just another test, and we're not going to do the computations for that one either. But I want to explain again, when you have a different design, when you do your research, when you get your graduate degree, you're doing research, or if you work in a lab and helping somebody do the research or work in a clinic, you'll have different designs, experimental designs. And so each of these tests line up with a certain design of an experiment. Okay, t-test, pretty standard. 2 groups, right? T for 2. Bum, ba-dum, ba-da-da-da-da, ba-dum, bum, ba-dum. Okay, T for 2. The 2 flavors here are between subjects, when you have different groups, and within subjects, using the same people, testing them twice. All right, I'll see you guys on Friday. Stay safe.